presentation, three, old and new. So please, you can.
So,
begin.
thank you for the presentation and thanks for the invitation. So, okay, what I'll speak about is about so some works I did on Anosov flows with Sergio Fenley. We have now several papers and still ongoing. And it is on the continuation of my PhD thesis, was done in 1992. And I met Sergio at that moment. It's more or less the moment I met Paul Schweitzer too, 30 years ago. So I realized now that when I met Paul, he had the age I have today. So maybe it makes me think that maybe I didn't reach half of my mathematical career. So, so what we deal with is that, so we have, as Rachel this morning on our talk, closed orientable three manifold. On this, we have some Anosov flow. It could be pseudo-Anosov, so the theory we are doing with Sergio, because of Sergio, is much concerned with the case of pseudo-Anosov flow. But we, a topological Anosov flow. We see more like the intersection between two transverse codimension one foliations, the stable foliation and the unstable wave. And the intersection is a one is a one-dimensional manifold, but with direction of time. Okay.
Thierry, probably.
No, but if I keep it that, it seems that okay.
Okay.
So it implies that the manifold, the existence of such a flow implies that the manifold is irreducible. Therefore, in the topological point of view, it admits what we call the Jacob-Shalen GG decomposition, meaning that we have a finite collection of embedded incompressible manifolds, tori, inside the manifold. And if we cut along this tori, the manifold have a finite collection of pieces, of connected components. Some of them are atoroidal, meaning that they admit some complete hyperbolic metric, or are ciphered, meaning that it admits a locally free action of the cycle. So you can think it as a second balls over some surface with boundary. So the question, actually what happens is that the GG decomposition match quite well with Anosov flow. So more or less the kind of question we have is that so we want, these tori, of course, are defined only up to isotopy in the manifold. So we just want to select the isotopy so that this tori will be in good position with respect. And the first step. And the second step is then to try to understand how the pieces of the Anosov flow inside every piece do behave. And we have really a quite complete description in the case where the piece is ciphered. When the piece is atoroidal, I don't know myself any very interesting thing. So first of all, so this is somewhere with Hi and Sergio, we finished this question in all of us had previous contribution on this question before, but it's almost 10 years ago. We have some good description about for this toroid. So let's just start with examples. The first example of Anosov flow are suspensions. So we take some Anosov diffeomorphism of the torus and we do product of the Anosov diffeomorphism. So in this manifold, we have transverse tori, which is good position. And when we here we just what we obtain after cutting by the transverse torus. So here there's only one piece, which is okay, you can see, which is well, of the GHG decomposition. But this one actually, from now, this case of suspensions is very special. So with starting from now, I will consider that M is not torus bundle over the circle. Actually, by the theorem of Planck, this kind of manifolds, the only Anosov flows or pseudo Anosov flows are these suspensions. We got Is it open? Yes, let us try. Is it okay? Or maybe with the macro it would be. Yeah. It is. Is it okay? Well, okay. No, so no problem. Okay. So the next example, if not a suspension with the classical one, it is geodesic flow. Is it okay for? Thanks. So you all know this picture. We have a surface equipped with a metric of Riemannian metric of negative curvature. And the flow is, well, I don't define anymore the geodesic flow, all of us you know. So on the surface, maybe if somebody asks, but here on the surface I selected, there's plenty of tori on this manifold, which is a tangent, the unit tangent bundle over the surface, which is three-dimensional. So every time you have a curve, a loop in the surface, you look at all the unit tangent vectors based at a point of this loop. So you obtain a circle, product of a circle, you obtain a torus. If you take a loop, a geodesic, so it gives you, in the direction, in this direction, you will have a periodic orbit of the geodesic flow, this one. And on the other orientation, you will have the other periodic orbit, which both lie in a given torus above this red loop. So it is parameterized by some angle, the angle from, let's say for theta, from this direction, going from 0 to pi. So you will have all the vectors pointing in the right direction. And the vectors pointing to the left direction will give us this part. So the torus is a union of two rings, annular. Sorry, thank you. Annuli. Each of them, so the periodic orbits are tangent to the flow, of course, but inside the annuli, each annulus, it is transverse, because if you start from here, you go in the direction, you will soon immediately leave the red curve. So it is transverse. So it's what we will call Birkhoff annulus. Like in the Anna Rechman's talk that she mentioned on this kind of annulus. And here I have depicted, remember that we have two foliations actually. I am interested more in these two directions, the foliations. And in this, if you do the analysis, you see that, let's say, stable leaves, so these codimensional foliations are transverse to the torus. And even these red loops, they are periodic orbit, so they are inside the weak leaves, so the stable foliation is transverse to the torus, and the unstable too. And these red curves are common, with a common intersection, okay? So inside these leaves, the stable leaves are spiraling from one periodic orbit to the other, like that. And the other unstable foliation is spiraling, but in the other direction. So we have this picture. Let us see an interesting example. This is, in some way, here I was assuming the surface to be orientable. Now assume that it is not orientable, and that this loop is a Möbius band. The tubular neighborhood is a Möbius band. So what happens? We have only one annulus. Okay, because we have no difference between this and this. If you go around the geodesic, you will go to the other side. So in this case, the annulus is going twice every periodic orbit. So actually here, so you have still two periodic orbits. Sorry, the picture is not good. I mean, you only have, so we have two periodic orbits. The annulus connect them, but around it, it's a Möbius band. Here it's a Möbius band. So together, it gives you a Klein bottle. So it will be a Birkhoff Klein bottle. And when you take a tubular neighborhood of this Klein bottle, what you get is an incompressible torus. You see? So it will be a good position too. Okay? So it's one of the cases I will list thereafter. Well, actually, I made a comparison with what Anna Rechman said, but actually, the situation here is not really the same. Not precisely. So, as Takashi Tsuboi said himself too, is that near the periodic orbit, when we consider a Birkhoff section, we usually ask for the Birkhoff section to wrap around the periodic orbit, to do like that. So that, you see, so it crosses the stable leaf, the unstable leaf, turning around. Here, it's not the case. This annulus does not, the only place it intersects the stable leaf of this curve is here, I mean, locally. So we are not wrapping around the periodic orbit. So that if you look at the annulus, here in this situation, the usual situation where we wrap around, the first rotor map is well defined, close to the periodic orbit. If you're close, you will meet another day, okay, the annulus. So you have some neighborhood like this, on outside here. But maybe at the interior of the annulus, you will never go back. Okay? So here we have a situation, you go back here, And if you have the frontier, you don't go back here. It's not good because les braves gens n'aiment pas qu'on suive une autre route qu'eux. So here, okay, this is my. So we will get interested in with this Birkhoff annulus in this sense, with not crossing the stable leaves. So I will do a picture from above. Every point represents some periodic orbits. And if I do that, I mean some Birkhoff annulus. So in your manifold, you may have a collection like that on periodic orbit, doing some graph. Okay? So each of us are Birkhoff annulus, transfer to the flow. I indicate here the way the flow is going through. And here is what we would call a spine. So it must be understood, so a Birkhoff annulus is embedded in the interior, but not at the boundary. It may wrap several times along the periodic orbit. Now I take a tubular neighborhood as such a thing. So you see the tubular neighborhood will be some surface with boundary. Product the circle, but maybe not exactly. It could be a Seifert here because of this wrapping thing, okay? So it will be typically a Seifert piece, okay? On such a Seifert piece, since the fibers are homotopic to periodic orbits, we say it is a periodic Seifert piece. So in some way, what we proved with Sergio is that if we have such a situation, then if you take all the periodic orbits, which are freely homotopic to this one, for example, we do this operation, we can do the Birkhoff annuli to be disjoint one from the other. And taking the tubular neighborhood, we will obtain exactly a piece of the GHG decomposition. Okay. Actually, this kind of situation happened in the examples of Bonanti-Langevin example. So in that case, there were only two annuli, but it was already the basis. So what we did with Sergio to generalize, which much better. Actually, there's a combinatorial structure. You just need, you see there is some combinatorial tree. We have the property about the degree of the vertices, things like that. It's going to be complicated. I don't enter these details. But there is we found a way to generalize this example in a much greater generality, so that actually we were able to prove some in the reverse direction. So I will start the theorem a bit later. But now I want to indicate this theorem. It was in the same paper. So we have some incompressible torus . So it might be one of the GHG decomposition, but not necessarily. It could be a torus inside some Seifert piece. And we try to put it in a good position. So the first case is a case which is a nice case. So you can either top the torus to some embedded torus, which is transverse to the flow, like in the case of suspension, or quasi-transverse, meaning admitting a finite number of periodic orbits tangent to the torus and transverse outside. So the second case is a boundary of a Klein bottle that I described before, previously, could happen. And the third case is that an immersed quasi-transverse in a periodic cipher piece. So it's, well, of course, not isotopic, it is homotopic, it means, but it could be something like that. You describe some loop in this graph, okay? So there's no way to make it embedded. So I think is the best answer to the first step we could do. And thanks to that, we can specify two tori which are in the GHG decomposition. So I look at tori, which has the boundary of a GHG piece. So it's a common boundary to one piece P1 and piece P2. I just take inclusion because these two pieces may have several different tori in their intersection. But anyway. So some Py could be hyperbolic or Seifert, but Seifert, we have two cases. It could be periodic Seifert or free Seifert. So periodic, it means that the Seifert piece has a fiber which up to a finite power could be freely homotopic to a periodic orbit of the flow. Here we say that for, it's not the case. Is a complement. No fibers are up to power, finite power, freely homotopic to periodic orbit. So there are some elementary Seifert pieces, like the tubular neighborhood of a Klein bottle, which admits several Seifert fibrations. It is very exceptional. But what we mean in this exceptional case that if for one fibration we have freely homotopic to periodic orbit, then we are periodic. Okay? So for example, finally you see the neighbor of the Birkhoff Klein bottle, if you take, it is you could see at a free piece as a part of a geodesic flow. But since the topology is quite simple, you have another cycle fibration over the Möbius band, a non-trivial one, then you are periodic in this point of view. Okay? So I don't enter more detail. So now, if your two pieces are autoidal, then for sure you are in case one. You can match the torus embedded in a quasi-transverse way. If the two pieces now are Seifert periodic, then you are case one, and actually it's more. You know that the torus can be transverse, not only quasi-transverse. So if the two pieces are free Seifert pieces, then you are in case 1, 2. And now we are quasi-transverse in a very special way I don't try to define here. If one piece is toroidal and P2 is free, we still are in case 1. So the only case it fails, we are not sure to be embedded, is that sorry, P1 toroidal, P2 is free, then we are in case 3. Okay. Actually, case 2, it means that it is a very, very special case. I don't want to discuss more. So, but here we are. No, it's a periodic. Sorry, periodic. Is what you meant, Brahmi, baby? No. Sure. Thanks. So we can do examples where exactly that happened, you know. So, okay. So now that we have understood how to put in good position, we can go inside. So only for Seifert pieces. I already mentioned, I will do, since time is running. Okay. If we have I already did what happens in the case of periodic Seifert pieces. And I gave more or less the idea of the proof. In this case, you have some periodic orbits, which up to a finite power are a power of the fibers. So you can define these annuli. And actually, you can construct so many of them that you recover the entire topology of the Seifert piece. Okay. So you have really a description how the flow behave. And actually, you see it's a very simple dynamic. It's like a Morse-Merle dynamic. You have a finite numbers of periodic orbits. And outside the flow, it just has a finite time existence. Okay. And we have a very explicit model to do like that, given the combinatorial data to recover the dynamic into this normal Seifert piece. So it attributes to a complete classification of totally periodic Anosov flow in graph manifolds. So Rachel Roberts this morning already mentioned what is a graph manifold. A graph manifold is a manifold in which all pieces, there is no toroidal piece. All pieces are Seifert. So here I'm assuming that all pieces are Seifert and periodic. And it is a complete classification. We can say 1, 2 of them are orbitally equivalent of these things. Now I want to finish to present what you have done recently, which were much more difficult. It's a case of free So in this case, it is a paper of 110 pages in geometry and topology, and I hope there is not too much mistakes inside, but I think so. But it was much difficult to do, and I don't want to try to describe it. It's simple to say. So after the good position for tori, we can say that we can describe a free periodic, a free Seifert piece as a piece of geodesic flow. Is what you obtain, for example, if you cut along, you talk in two parts. Every part, so the unit tangent bundle over it, give you an example of free Anosov foliation, because it's not a flow anymore, it's oriented foliation. And we can have a description with the two foliations. It's only for the flow, but for each stable weak foliation, the stable foliation, the unstable foliation. But it's not exactly true, because actually you can do some blow up. Once again, as I explained recall this week, you can open along a leaf. So, and to create some, let's say, Danjois gaps, okay? So it's still possible to do that. But in order to finish, in a parallel way to this theorem of totally periodic, you have the case of totally free Anosov flow on graph manifolds. So once again, it means, so I assume that I have a graph manifold, and all pieces are free. Of course, there are mixed cases. We have examples where you may have pieces which are free over periodic, okay? But in the case it is totally free, then our theory allows us to prove that it is, all of them are generalized under Thurston. So we'll explain that a bit more. So actually, it was the end of my PhD thesis 30 years later, because it was the initial question in some way. But there was still some question who has trickled me, and that we recently succeeded to solve with Sergio. So we'll try to explain that. So first of all, let us explain what is Handel-Thurston example. So you must have, maybe some of you already know. Take this situation. Take this torus above this red curve. Cut along this torus and glue back, but now adding some then twist in a positive direction. Okay? So you will not have anymore a cycle bundle, but really a graph manifold. And Handel-Thurston proved that you can do this in such a way that the flow is still Anosov. And it is exactly one example of totally free Anosov flow on a graph manifold with two free pieces. Okay. Let us just mention that in 2017, Fuller and Hasselblad proved that moreover we can do it, this construction, in order to get a rib Anosov flows, meaning you have a contact form, and the Anosov flow is a rib flow of this contact form. Okay. So of course you can do it not only for the flow but for your finite cover. And here is the problem I want to present to you, which is arithmetical problem that maybe puzzled some of you from the beginning, which is related to that. If you take a finite cover of the geodesic flow, you will still have such quasi-transverse tori, but maybe you will have more than two periodic orbits. You will have a even number of periodic orbits, but not necessarily two. It depends on the covering you do, okay? And then you can glue back and you still have some examples. What was not very clear in the paper by Handel-Thurston is the following problem. You could take a finite number of, let's say, pair of points, or not necessarily, but anyway, surfaces with boundary. Here, genus 1, okay? Take a finite covering of for each of them. Let's say a finite order on index n1 here, finite cover index n2. You may have more than 2 pieces, of course, you may have, okay? We do only covers along the fibers, okay? So actually, to define such a cover, you need some integers to define the covers with a property I don't want to enter in these details, but to do such a cover along the fibers along such a surface, it means that you have to select 3 in here we have 3 connected components of the boundary, so we have 3 integrals. You want the sum to be related to the Euler characteristic. Okay, and you do the same thing here. And now you can try to glue, let's say, this torus, quasi-torus to this one, and to this one. Okay? Of course, what you need is that the number of periodic orbit here has to be the same as the number of orbit periodic here, because you want to glue in a coherent way. So the number so there is always an even number of periodic orbits, because okay, you have in every direction. So of course, if the index is the same, you can do it. It just means that you take a finite cover of the initial unit tangent bundle. The question is it possible if the index are different? Okay? So what we proved is that we generalized in some way under Foston techniques, but maybe they were already aware. They had a very quick way to express it. It was not clear if we had this problem in mind. Maybe yes, maybe not. But anyway, we have been able to prove that if we have the same, this obstruction to have the same number of periodic orbits to be glued, if it's okay, then you can do the gluing so that the resulting flow is still Anosov. On moreover, it is a contact. So maybe it's slightly more than under Foston, okay? So the question is now, is it possible? What you see? So here is a problem. You fix the genus of the surface. You fix the number of boundary components. You need at least one to do some gluing. And you prescribe the number of periodic orbits you want in which over each boundary component. So the question, can you find some index n on integers giving the finite cover? So you need this condition, and you want on the number of periodic orbits is a common greater divisor of n on ui. So you see, this kind of problem, I don't know how to solve it. Even in the case of pair of points, you have 3 integers, the sum of which is 1. I have L1 and 2, L3. Can I realize them as a common greater divisor between ny, nu y and some integral n? Okay. So I think I'm at the end of the talk, so I will stop here. Thanks for your attention.
Some questions or comments?
Could you explain a little bit more this last construction and
the problem here about
yes,
this one?
That's
yeah.
right.
So okay, just so If I take the final cover of a compact, non-closed with boundary, surface with boundary, we know that it is we have some trivialization. So it is homomorphic to the surface product the circle, right? We know that. But you have different trivialization. Trivialization means to find some section. And we have many, many different sections. So a way to express, so to be less mysterious, if you take, so you take an orientation of the surface, so C1, C2, C3, then above each boundary component, you have a natural canonical section, which is just the unit tangent in this direction, okay? Sure. So now if you want another one, you say you can add to each of them some, so I call it C1 bar, C3 bar, C2 bar, the loops in the unit tangent bundle. Now any other loop above it, it's just this one, plus some integers, the fiber, in homology, right? So if you want, so now that you have selected some loop above, thanks to these integers, so you want these loops to be the boundary of some surface, of some section. So you want that the sum of them is trivial in homology. And it leads you to this condition, which is okay.
More comments or questions? No? What do you expect about the mixed case with periodic and free cipher pieces?
Well, we have examples. Actually, we have nice examples, actually, which we didn't think that a lot, maybe. We wanted to finish. I mean, this theorem is a theorem in 2023, you know. So, but maybe the next step will be to think more. But we already have examples. We can see the fact that now it could be more complicated, but because this blow-up phenomenon is appearing. So I don't have a precise statement in my mind now.
Okay. So let's thank the speaker again.